Hi class, we are now on 10.6. We are on the last section of this chapter, and this is using stoichiometry, balanced equations, and expanding on gas calculations that we've done. So sudden changes in gas pressure can have explosive results. These changes often arise when gases form or are consumed in a chemical reaction. To safely conduct reactions involving gases, we must know how much gas is produced or consumed. For example, the process of fermentation used in beer and bread involves the reaction of glucose to form ethanol and carbon dioxide. To conduct this reaction safely, we need to be aware of how much gas is being produced. For example, in this fermentation reaction, how much carbon dioxide is produced for each kilogram of glucose that reacts? To answer a question like this, we must combine the rules of stoichiometry, which is from chapter 7, with the gas laws. So at the center of these two concepts is the mole. Using the ideal gas law, we can relate pressure, volume, and temperature to the number of moles of a gas. So in this chapter, we first talked about a mole map that showed the relationships between grams and moles, particles, and the balanced equation. Now we can expand that map to include gases as well. Using this map, we can chart a path from any reactant or product in a balanced equation to any product. We can relate grams, moles, particles, or any substance. For gases, we can use the pressure, volume, temperature to determine how much of a reactant is consumed and how much product will form. So if we take a look at this problem right here, or should I say example. So in the fermentation of glucose, how many moles of carbon dioxide are produced from each kilogram of glucose that reacts? If the reaction takes place in a sealed container and the gas occupies a volume of 8.10 liters at a temperature of 21 degrees Celsius, find the pressure of carbon dioxide gas inside the container. To solve this problem, we first relate grams of glucose to moles of carbon dioxide. Following the mole map, our strategy is to go from grams of glucose to moles of CO2. We begin with 1 kilogram, that's 1,000 grams, of glucose times 1 mole per 180.18 grams of glucose times 2 moles of CO2 per 1 mole of glucose. This gives us 11.10 moles of carbon dioxide. Once we found the moles of carbon dioxide, we can use the ideal gas equation to find the pressure. We be sure to convert the temperature to kelvins and then solve. And so here we can see we have it isolated for pressure. We then plug everything in with the gas constant, the Kelvin, and temperatures. Here you can see where we got the temperature. And the answer is 33.1 atm of carbon dioxide. A pressure of 33.1 atm is a dangerous explosion risk. To prevent this risk, brewers must be careful to release some of the CO2 formed and to monitor the pressure inside the fermentation vessels. Let's do another one. Natural gas burns cleanly in air according to this equation. Methane plus oxygen in the presence of oxygen produces CO2 and water vapor. If 13.1 liters of methane burn at a pressure of 1 atmosphere and a temperature of 290, what mass of carbon dioxide gas is produced? In this question, we're given the pressure and the volume. Our first step is to convert this to moles using the ideal gas equation. So we set it up to determine what the moles are. So we determine that the moles are 0.550 moles of methane. Once we have the moles, we use the balanced equation to relate this to the moles of CO2 and then the grams of CO2. So we set it up with 0.55 moles of methane. We can see that it's a 1-to-1 ratio, which is what we set up, and then the molar mass. And this produces 24.2 grams of CO2. This does involve several steps. You might have to take your time because this is, it's not easy in the beginning to do this, and it's really easy to make a mistake. So we use the ideal gas law to relate pressure and volume to the moles of substance. Once you have the moles, you can relate it to the moles of any substance in the equation using the balanced equation. So this can kind of show you how you can go from one thing to another. All right, so let's now look at some problems. The reaction of potassium metal with water produces hydrogen gas. how many moles of hydrogen gas can be produced from 5 moles of potassium? So that's a normal, we can try to figure out just by doing the stoichiometry here. We can take the 5 moles of potassium, set it up with the balanced equation, and it tells us that we produce 2.5 moles of H2. But now the second question is, in STP conditions, how many liters of hydrogen can be produced? So we set up the ideal gas law equation, we solve it for V, and then we can plug everything in, which is what you see here. We have the moles from his equation. Now this is STP. So that's pressure is 1 atm and temperature is 273. We use the gas constant. And this is 56.03 liters, and the correct answer is 56.0. What strategy would we use to find the grams of water that could be formed from 45 moles of HF? Well, if you have 45 moles, the first thing you need is to go to moles, and then moles of water to grams of water. So if we find that, it would be A. What volume of carbon dioxide is formed with 0.5 moles of butane? Burns in excess of oxygen at STP. So we're dealing with standard temperature and pressure conditions. So the first thing we do is what is related from chapter 7. We set it up with the butane, and we determine what the moles of CO2 are. We then plug that in because it's asking for the volume. So we isolate volume, plug everything in. We take that answer. Here we go. STP is 1 atm and 273 is the temperature, and this gives us 44.82 liters. 0.2 moles of hydrogen gas and 0.1 mole of oxygen gas react in a sealed 2.0 liter container. If the temperature is in the container is 400 K, what is the total pressure of the gas after reaction? So you're given two different amounts, and you're going to have to see which one produces the most or the least. Either one is going to tell you which is the limiting. So in this case, when I did it, they both came out with the same answer of 0.200 mole. So that's going to be what I'm going to use on the bottom one. So, but had you had something different, you would treat it like a limiting because the reaction won't go anymore. You have to use the smallest amount. The reactant that produces the smallest amount. So in this case, they both came out with the same answer. So in this one, I plug it in. We solve for pressure. It ends up giving us a pressure of 3.284, and that rounds down to 3.28 atm. Nitrogen monoxide, a component of air pollution, can be removed from the atmosphere by reaction with ammonia. What mass of ammonia is required to completely react with 25 liters of nitrogen monoxide at STP? So here we are with STP again. So the first thing we need to do is we're told that it needs to be we want to know the mass of ammonia that's required to, what mass of ammonia is required to completely react with 25 liters of nitrogen monoxide. So the first thing we need to do is we need to determine the moles of NO. We can't determine the mass until we can get to NO. So we need to use that 25 liters, plug it into the ideal equation, and determine what the moles are. In STP conditions, again, 1 atm, 273 liters. It's giving us the volume. So we plug that in. It gives us 1.11 mole NO. Now we're going to do what we've been doing, and it looks like I accidentally forgot to finish this one here. This is 1 mole of NH3. So you can see we plug it in, and this should have 1 mole here because it's molar mass, and it comes out with 12.59 grams of ammonia. Nitrogen monoxide, a component of air pollution, can be removed from the atmosphere by reaction with ammonia. If 10 grams of ammonia reacts with excess nitrogen monoxide at 218 and 225 millimeters mercury, what volume of nitrogen gas will form? So we go through, and we start with ammonia, and we work this. It looks like it moved over a little bit, and it gives us the moles of nitrogen, because we want to know about the volume of nitrogen gas. So we're going to need to get to moles of nitrogen, which is what we do here. So based on the 10 grams, we get to the moles. From here, we can plug in the moles when we isolate volume. Everything, here we have we've converted the millimeters mercury into ATM, so we can use the correct gas constant, and it produces 44.35 liters of NO, which results in 44.4